nth roots of unity. So we're doing the same thing we just done. We just found the roots of a complex number. However, when we see the word unity, it's referring to the unit circle. So in other words, the modulus is 1. Okay, so that's what unity means. Okay, so we can have our solution find the nth roots of unity. So we're really finding the nth root of plus or minus 1. Okay, around the unit circle. Okay, so in other words, when we put the roots on there, okay, the n roots, like we've seen before, will fit around the unit circle with modulus 1, and if we were to join up the roots, okay, they will form a regular polygon of n sides. Okay. Right, so find the 5 fifth roots, okay, of unity of 1 and plot the results in the unit circle. Okay, so when you're told the 5 fifth roots, we're saying that z to the power of 5 is 1. Okay, so we already know the modulus because of the unit circle, so the modulus is 1. Okay, and the argument. Alright, so the argument, tan inverse of the imaginary part over the real part, so the imaginary part is 0, over the real part 1, so tan inverse of 0 is, nope. Logically, what's tan inverse of 0? Zero. Have you seen a tan graph before? Yeah, what is a tan graph before? Something like that. Asymptote there, asymptote there. Right, so tan of 0 degree is going to be 0 for YB. Okay. So, going back to the formula there. Okay, so we're using that same formula. However, if n roots of r, it's always going to be 1 because you're referring to the unit circle. Okay, so it's going to be cis. Now it's 2 pi k plus theta over n. Okay, so theta is 0. So we're going to be 2 pi k over your 5 roots you need to find. Theta is 0, so I'm not including that in my formula. Now, 0, oh sorry, k, not z. K is 0, plus or minus 1, and plus or minus 2. Because our solution, our complex solution, occurs in conjugate pairs. Alright? So I can use this technique here. Alright, so when k is 0, z 0, it's going to be cis of 0, so cos of 0 is one. Sine of 0 is 0, so z0 is 1. K is 1, Z1 is going to be 2 pi times 1 over 5. Okay, so we're going to be 2, cis of 2 pi. Okay, K is negative 1. Z2 is going to be cis of negative 2 pi. Sorry. Yep. Cis of negative 2 pi on 5. Yep. Because we're substituting in for the vector K. K is 2, Z3. Just ordering roots in chronological order. Cis of 2 pi times 2, so 4 pi on 5. And k is negative 2, z3, z4, sorry. It's going to be cis of negative 4 pi on 5. Okay, because your solution for your, if one solution is complex, then your solutions will always be represented in conjugate pairs. Alright, so I'm using that theory to graph that. Okay, so the modulus is 1. So our first solution, z0 is 1. So it's 1 on the real part. There. Okay, 2 pi on 5. So we've got 360 divided by 5, which is 72. Right. And we have the flip on the x-axis for your conjugate pairs solution. Okay, so in other words, take away 2 pi on 5, so you're going around 2 pi on 5 this way, and negative 2 pi on 5, you're going to have the same vertical alignment of your solution. So Z1, Z2, okay, and they're spaced around the unit circle. In other words, there's a separation of 72 degrees between two solutions, two of your roots. So somewhere here and here, so Z3 and Z4. Okay, so if I were to draw the circle that it forms, the 5 roots form a circle, and I can join the roots and it becomes our regular 5-sided, well, regular polygon. Of course, polygon has 5 sides. Okay, so it's a little handy feature, okay, to remember that conjugates are a solution occur in conjugate pairs. You can go 0, 1, 2, 3, 4, okay, it just means you're going to have to do a 2 pi takeaway to get it back into an angle between 0 and 2 pi so you can plot it. Alright, so that's why I've used that technique there. Alright, B. If omega, so W is the Greek letter of the alphabet, is omega, looks like a W, okay, is a complex root of the equation x to the power 7, take away 1 equals 0. We need to show that the other complex roots are W, omega 2, W, omega 3, omega 4, omega 5, omega 6 is actually omega 7 as well. Error, omega 7, because we're expecting 7 roots. Okay, so we've got one of them here. We're assuming that the omega is one of them. We're going to show that omega squared, omega cubed, all the way up to omega 7 for our 7 roots, okay, are also the other complex roots. Okay, once we've done that, we're going to show that, prove that result. Can we put a W, so plus 1 plus omega squared plus omega cubed plus omega to the power 4 plus omega to the power 5 plus omega to the power 6 is equal to 0. Okay, so we have x to the power 7 is equal to 1 from the equation there. Okay, so just moving 1 on the other side because we're finding the seventh roots of unity there. Okay, so if omega is a solution, okay, so that must mean that omega to the power of 7 is equal to 1. Okay, so substituting your root, it must match your equation of what you're doing. Okay, or in other words, omega to the power of 7 take away 1 is 0. Okay, so omega 7 is equal to 1. So if we substitute that root, omega 7, into the equation here, okay, so we know that omega 7 is to the power of 1, omega to the power of 7 equals 1. So if I substitute that again into my equation, so if I'm assuming the root is omega to the power of 7, and I'll take that to the power of 7, okay, so 1 to the power of 7 is also 1. And that matches my equation, because 1 take away 1 is 0. That is also a solution. Okay, so now I need to show that omega squared, 3, omega 3, and so forth are also the roots. Okay, so let's start with, we've already assumed omega, so omega squared. So if we substitute that into this equation, take away 1. Okay, this equals, using your index laws, omega to the power of 7 squared, so you're swapping these around using the index laws because you're multiplying. Take away 1, the omega to the power of 7 that we've already established is 1. So 1 squared, take away 1, which is 0. Okay, omega cubed, substitute that into your equation, power of 7, take away 1, and then we're going to swap your powers around. So omega to the power of 7, or to the power of 3, take away 1. And again, we know what omega 7 is. Okay, we've already established that's 1. So 1 cubed, take away 1, which is 0. Alright, and we continue that pattern right through until we get up to omega 6, on omega to the power of 6. Okay, so continuing pattern, etc. So continuing the pattern the roots are omega, omega squared, omega cubed, omega to the power of 4, omega to the power of 5, omega to the power of 6, and omega to the power of 7. Okay, so just go omega to the power of 4, omega to the power of 5, omega to the power of 6. Do the same setup. And it will always equal 1. Okay, they're also the complex roots. Okay. So we've shown the other roots. Now we need to prove that 1 plus omega squared up to omega to the power of 6 is equal to 0. Okay, so we're required to prove 1 plus omega squared plus plus omega to the power of 6 is equal to 0. Okay, so let's go back one step. So omega plus omega squared plus omega cubed. So we're getting my 7 roots. I'm adding them all together. What do you remember about adding roots together? Sum of the roots equals negative b over a. Okay, remember the equation is x to the power of 7, take away 1 is 0. So what's b? What's a? 1, what's b? B is the coefficient of what? X to the power of 6. What's the coefficient of x to the power of 6? A, x to the power of 6 would be b, x to the power of 5 would be c, x to the power of 4, and so forth. There is no x to the power of 6, so the coefficient must be 0.
Are you saying that there's no x?
Just power of 6. There's no x to the power of 6.
The polynomial is x to the power of 7 take away 1.
Oh, so there's only a and c.
A and A, B, C, D, E, F, G. A and G.
So x squared, x to the 7 minus 1 is a and g.
No.
What do I
The
know?
pattern always follows. Negative b over a, sum roots 1 at a time. C on a, sum of the roots 2 at a time. Negative d on a, sum of the roots 3 at a time.
But the only coefficients are 1.
Because that's a, isn't it? The highest power is a. The next power down is b. The next power down is c.
So
It's just a massive
it's
polynomial.
a and g. It's a and g.
Just a and g as you see here, yes. So b is 0.
Yeah.
Alright, so sum of the roots 1 at a time must equal 0. Okay, so what we're showing 1 plus omega squared plus omega 6 up to is 0. What are we missing from that line that we've got in this line?
7.
Omega 7. What's omega to the power of 7?
1.
1. So, and omega to the power of 7 is 1. So therefore, 1 plus omega squared plus dot 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 plus omega to the power of 6 is 0. Done.